Hello and welcome to Neptune Files. Tonight we're leaving Earth. Not in a rocket, not in a spacecraft, but in the mind. We're going to travel outward, step by step, from the ground beneath your feet to the farthest edge of everything that can ever be seen, the edge of the observable universe. It's a journey that covers 46 billion light-years in every direction. A distance so staggering that even the word distance starts to lose its meaning. But we're not going to rush. We're going to take it slowly, gently, letting each step sink in before we move on to the next. So settle in, close your eyes if you'd like, and let's begin the longest journey it's possible to take. Right now, you're lying somewhere on the surface of the Earth, a planet 12,742 kilometers across, spinning on its axis at about 1,670 kilometers per hour at the equator. You don't feel the spin. You don't feel the speed. The ground beneath you feels perfectly still, perfectly solid, as though it has always been here and always will be. But the Earth is moving. It's spinning, yes, but it's also hurtling through space, orbiting the Sun at roughly 107,000 kilometers per hour. And the Sun itself is moving, carrying the Earth and all the other planets along with it, orbiting the center of the Milky Way galaxy at about 828,000 kilometers per hour. And the Milky Way is moving too, drawn through intergalactic space by the gravity of distant galaxy clusters at about 2.1 million kilometers per hour. You are, right now, in this quiet moment, traveling at an almost incomprehensible speed through the cosmos. But you feel none of it. The air is still, the room is quiet, and the stars, if you could see them, would appear perfectly fixed in the sky, as they have for every human being who has ever lived. Let's start our journey by looking at the ground. The Earth's crust, the thin rocky shell we live on, is just 5 to 70 kilometers thick, depending on whether you're standing on oceanic crust or continental crust. Beneath it lies the mantle, 2,900 kilometers of slowly flowing rock. Beneath that, the outer core, a churning ocean of liquid iron and nickel. And at the very center, the inner core, a solid ball of iron about the size of the moon, compressed to incredible density by the weight of everything above it, heated to about 5,400 degrees Celsius. The Earth is alive, geologically speaking. It is hot and dynamic and restless, but from up here on the surface, it feels serene, steady, home. Now let's lift off, not fast, just gently, rising above the surface, leaving the ground behind. At 1 kilometer up, you can see the curvature of the landscape, the way fields and forests and roads spread out beneath you. At 10 kilometers, roughly the cruising altitude of a commercial airplane, the sky begins to darken above you. The air is thinner here, colder. Below, the Earth's surface stretches to the horizon, blue and brown and white with clouds. At 100 kilometers, you've crossed the Kármán line, the internationally recognized boundary of space. Below you, the atmosphere is a thin, luminous band, a fragile shell of gas clinging to the planet's surface. Above you, the sky is black. Stars appear steady and unblinking because there's no atmosphere to make them twinkle. You are in space, but you've barely begun. 100 kilometers is nothing. It's less than the distance from London to Birmingham, from New York to Philadelphia. The International Space Station orbits at about 400 kilometers above the Earth's surface, close enough that astronauts can see individual cities, coastlines, and storms. At this altitude, the Earth still dominates the view. It fills the window, vast and curved and heartbreakingly beautiful, a blue marble wrapped in swirls of white, floating in the darkness. Every astronaut who has seen the Earth from orbit reports a profound shift in perspective, a feeling sometimes called the overview effect. The borders between nations, visible on maps, are invisible from space. The atmosphere, which seems so vast when you're standing beneath it, is revealed as a paper-thin membrane. And the Earth itself, which feels so permanent and so large, is revealed as a fragile, isolated sphere floating alone in the void. Let's keep going. At about 35,786 kilometers above the equator, we reach geostationary orbit, the altitude at which communication satellites orbit the Earth at exactly the same rate it rotates, appearing to hover motionless above a fixed point on the surface. From here, the Earth is smaller. You can see entire continents at a glance. Africa, South America, the Pacific Ocean, impossibly vast, covering nearly half the planet. The atmosphere is a barely visible film at the edge of the globe, so thin it seems impossible that it could sustain all the life below. At about 384,400 kilometers from Earth, we reach the Moon, our nearest celestial neighbor, a barren, airless, cratered world about a quarter the diameter of Earth. The Moon is the only other world that human beings have ever walked on. 12 people, all American astronauts, set foot on its surface between 1969 and 1972. They found a landscape of fine grey dust, sharp-edged craters, and utter silence. No wind, no sound, no life. Just the ancient battered surface of a world that has been pummeled by impacts for 4.5 billion years, with no atmosphere or water to erase the scars. The distance from the Earth to the Moon, about 384,400 kilometers, is a useful starting point for understanding cosmic distances. Light, the fastest thing in the universe, covers this distance in about 1.28 seconds. When you look at the Moon in the night sky, you're seeing it as it was 1.28 seconds ago. That delay is imperceptible. But as we travel farther out, the light travel time will grow, and it will teach us something profound about the nature of the universe. Looking outward is looking backward in time. Here is a fact that helps put this distance into perspective. If you could line up Earths side by side between here and the Moon, you would need about 30 of them. The gap is large enough to fit every other planet in the solar system between the Earth and the Moon, with room to spare. Jupiter, Saturn, Uranus, Neptune, Mars, Venus, and Mercury, all stacked together, would fit in that gap. And yet, on the scale of the solar system, the Earth-Moon distance is tiny. A short stroll across the front porch. Now let's leave the Earth-Moon system and travel deeper into the solar system. Our first landmark is Venus, Earth's nearest planetary neighbor, at its closest approach about 38 million kilometers away. Venus is often called Earth's twin because of its similar size and mass, but the resemblance ends there. Venus has a thick atmosphere of carbon dioxide with clouds of sulfuric acid, a runaway greenhouse effect that has raised the surface temperature to about 465 degrees Celsius, hot enough to melt lead. The atmospheric pressure at the surface is about 90 times that of Earth, equivalent to the pressure a kilometer deep in Earth's oceans. Soviet landers that reached the surface in the 1970s and 1980s survived for only minutes before being crushed and cooked. Venus is a reminder that a planet's size and distance from its star don't guarantee habitability. Small differences in atmospheric composition can lead to radically different outcomes. Then Mars, which at its closest is about 55 million kilometers from Earth. Light takes about 3 minutes to travel from Mars to Earth at that distance. When NASA engineers send a command to a rover on Mars, they have to wait at least 3 minutes for the signal to arrive and another 3 minutes for the response to come back. A 6-minute round trip at the speed of light. In the vastness of space, even light takes time. Mars is a cold, dry, dusty world with a thin atmosphere of carbon dioxide, about 1% the density of Earth's. But it wasn't always this way. Billions of years ago, Mars had a thicker atmosphere, liquid water on its surface, rivers and lakes, and perhaps even a northern ocean. The evidence is written in the landscape, in dry riverbeds and lake deposits, and mineral formations that can only form in the presence of water. What happened to Mars's water and atmosphere is one of the great questions of planetary science. The leading theory is that Mars, being smaller than Earth, lost its internal heat more quickly, its magnetic field weakened, and the solar wind gradually stripped away its atmosphere over hundreds of millions of years. The water evaporated, was lost to space, or froze into the ground. Mars became the cold desert we see today, but beneath its surface, some of that ancient water may remain, locked in permafrost or underground aquifers. And where there is water, there might, just might, be life. Let's keep going. Past the asteroid belt, a region between Mars and Jupiter populated by millions of rocky bodies, remnants of the solar system's formation that never coalesced into a planet, prevented from doing so by Jupiter's enormous gravity. The largest asteroid, Ceres, is about 940 kilometers across and is classified as a dwarf planet. Most asteroids are much smaller, ranging from boulders to objects a few hundred kilometers across. Despite the dramatic depictions in science fiction, the asteroid belt is mostly empty space. If you flew through it, you'd be unlikely to see a single asteroid with the naked eye. The total mass of all the asteroids combined is less than 4% of the mass of the Moon. Past the asteroid belt, we reach Jupiter, the largest planet in the solar system, a gas giant 11 times the diameter of Earth, with a mass greater than all the other planets combined. Jupiter orbits the Sun at about 778 million kilometers, and light takes about 43 minutes to travel from the Sun to Jupiter. Jupiter is a world of storms. Its atmosphere is banded with clouds of ammonia and water, driven by winds of up to 640 kilometers per hour. The Great Red Spot, a storm larger than Earth, has been raging for at least 350 years, possibly much longer. Recent observations suggest it may be shrinking, but it remains one of the most dramatic features in the solar system. Jupiter has at least 95 known moons, including the 4 large Galilean moons discovered by Galileo in 1610. Europa, one of these moons, is one of the most tantalizing worlds in the solar system. Its surface is a shell of ice, smooth and young, crisscrossed by reddish-brown fractures that suggest the ice is being constantly resurfaced. Beneath this ice shell lies a global ocean of liquid water, kept liquid by tidal heating, the gravitational flexing caused by Jupiter's immense gravity. This ocean may contain more water than all of Earth's oceans combined. And where there is liquid water, there is the possibility of life. NASA's Europa Clipper mission, launched in 2024, is designed to study Europa's ice shell and ocean in unprecedented detail, searching for the chemical signatures that might indicate a habitable environment. Another of Jupiter's moons, Io, is the most volcanically active body in the solar system. Its surface is covered with hundreds of active volcanoes, some of which shoot plumes of sulfur and sulfur dioxide hundreds of kilometers above the surface. The volcanic activity is driven by tidal heating from Jupiter's gravity, which flexes Io's interior and generates enormous amounts of heat. Io's surface is a hellscape of lava flows and sulfurous deposits, constantly being reshaped by eruptions. It is one of the most dynamic and violent places in the solar system, a world in perpetual geological turmoil. Ganymede, the largest moon in the solar system, is bigger than the planet Mercury. It has its own magnetic field, the only moon known to have one, and may also have a subsurface ocean beneath its icy crust. Callisto, the outermost Galilean moon, is one of the most heavily cratered objects in the solar system, its ancient surface a record of billions of years of impacts. Past Jupiter, we reach Saturn, the ringed planet, orbiting at about 1.4 billion kilometers from the Sun. Light takes about 79 minutes to reach Saturn from the Sun. Saturn's rings, made of billions of particles of ice and rock ranging from tiny grains to house-sized boulders, are one of the most stunning sights in the solar system. They extend hundreds of thousands of kilometers from the planet but are remarkably thin, only about 10 meters thick in most places. If you could shrink Saturn's rings to the diameter of a football field, they would be thinner than a razor blade. The rings are not permanent. They are slowly losing material, raining ice particles into Saturn's atmosphere. Some estimates suggest the rings may be only 100 to 200 million years old, meaning they may have formed long after the dinosaurs went extinct on Earth. If this is true, then Saturn spent most of its 4.5 billion year history without rings, and future observers, millions of years from now, may see a ringless Saturn. We are perhaps living in a lucky window of cosmic time. Saturn's moon Titan is the only moon in the solar system with a thick atmosphere. Its surface, hidden beneath orange haze, is a landscape of hydrocarbon lakes and rivers, dunes of organic material and ice mountains. It rains on Titan, but the rain is liquid methane, not water. The rivers flow with ethane and methane, carving channels and filling basins in a hauntingly Earth-like hydrological cycle, but with a chemistry utterly alien to our own. Titan's atmosphere is mostly nitrogen, like Earth's, but the temperature at the surface is about -179 degrees Celsius, so cold that water ice behaves like rock and methane behaves like water. Another of Saturn's moons, Enceladus, has become one of the most exciting targets in the search for extraterrestrial life. This small, ice-covered moon, only about 500 kilometers across, has geysers at its south pole that shoot plumes of water vapor, ice particles, and organic molecules hundreds of kilometers into space. The Cassini spacecraft flew through these plumes and detected molecular hydrogen, a potential energy source for microbial life, along with complex organic molecules. Beneath Enceladus's icy surface lies a global ocean, heated by tidal interactions with Saturn. The combination of liquid water, organic chemistry, and an energy source makes Enceladus one of the most promising places in the solar system to search for life beyond Earth. Farther out still, Uranus orbits at about 2.9 billion kilometers from the Sun, and Neptune at about 4.5 billion kilometers. Light from the Sun takes about 4 hours to reach Neptune. These ice giants are cold, distant, and mysterious. Uranus rotates on its side, its axis tilted nearly 98 degrees, so that it essentially rolls around its orbit. This extreme tilt may be the result of a collision with an Earth-sized object early in the solar system's history, a cosmic accident that knocked the planet onto its side. Uranus has a bland, featureless appearance in most images, but beneath its calm blue-green exterior, there are powerful winds and a strange internal heat deficit. Uranus radiates less heat than it receives from the Sun, unlike all the other giant planets, and no one is entirely sure why. Neptune, the farthest planet from the Sun, is a deep blue world with the fastest winds in the solar system, gusting up to 2,100 kilometers per hour. The source of these extreme winds is a puzzle, because Neptune receives very little energy from the Sun. The planet radiates about 2.6 times as much energy as it receives, suggesting a powerful internal heat source. Neptune's moon Triton orbits in the opposite direction to the planet's rotation, suggesting it was captured from the Kuiper Belt, a vast ring of icy bodies beyond Neptune's orbit. Triton has geysers of nitrogen gas that erupt from its surface, and it may have a subsurface ocean. It is one of the coldest known objects in the solar system, with a surface temperature of about -235 degrees Celsius. Past Neptune, we enter the Kuiper Belt, home to Pluto and thousands of other small, icy worlds. Pluto, reclassified from planet to dwarf planet in 2006, orbits at an average distance of about 5.9 billion kilometers from the Sun. When the New Horizons spacecraft flew past Pluto in 2015, it took about 4.5 hours for the data to travel back to Earth at the speed of light. The images it returned were stunning: a world of nitrogen ice plains, mountains of water ice as hard as rock, and a thin atmosphere of nitrogen and methane. Pluto's largest feature, a heart-shaped plain called Sputnik Planitia, is a vast basin filled with slowly convecting nitrogen ice, a geological process that is still active today. Even here, at the frigid edge of the solar system, there was complexity, there was geology, there was beauty. In 2017, an object from outside our solar system was detected for the first time. Called Oumuamua, a Hawaiian word meaning scout. It was a small, elongated object that passed through the inner solar system on a hyperbolic trajectory, meaning it was not gravitationally bound to the Sun. It came from interstellar space and was heading back out. Its exact nature remains debated. Some astronomers believe it was a fragment of a nitrogen ice planet from another star system. Others have proposed more exotic explanations. Whatever it was, Oumuamua was the first confirmed interstellar visitor, proof that objects from other star systems can and do wander through our own. But the solar system doesn't end at the Kuiper Belt. Far beyond lies the Oort cloud, a theoretical shell of icy objects that may extend from about 2,000 astronomical units to as far as 100,000 astronomical units from the Sun. An astronomical unit is the average distance from the Earth to the Sun, about 150 million kilometers. So 100,000 astronomical units is about 15 trillion kilometers. Light takes about 1.6 years to cross the Oort cloud at its outer edge. This is where long-period comets come from, icy bodies that take thousands or millions of years to complete a single orbit, plunging inward toward the Sun and then retreating back into the darkness. The Oort cloud marks the outermost gravitational reach of the Sun. Beyond it, the Sun's influence fades and interstellar space begins. We have left the solar system, and we've traveled about 1.6 light-years to get here. But the nearest star is still more than twice that distance away. Let's pause for a moment, take a breath, feel the quiet of the room around you. We've traveled from the surface of the Earth to the edge of the solar system, a distance that light takes about 1.6 years to cross, and yet on the scale of the universe, we've barely moved. The solar system is unimaginably vast by human standards, but it's a speck, a tiny island of warmth and light in an ocean of cold, dark, empty space. The distances that come next will make everything we've covered so far seem like a short walk across the room. The nearest star to our Sun is Proxima Centauri, a small red dwarf about 4.24 light-years away. That's about 40 trillion kilometers. Let's try to make that number feel real. If you could drive a car at highway speed, 100 kilometers per hour, without stopping, it would take you about 45 million years to get there. If you could fly at the speed of the fastest spacecraft ever launched, NASA's Parker Solar Probe, which has reached speeds of about 635,000 kilometers per hour, it would still take about 7,000 years. Even at the speed of light, the fastest speed possible in our universe, it takes 4.24 years, more than 4 years of non-stop travel, at 300,000 kilometers per second to reach the nearest star. Here's another way to think about it. If the Sun were a grapefruit sitting on a table in front of you, the Earth would be a grain of sand about 15 meters away. Jupiter would be a peppercorn about 77 meters away. And Proxima Centauri would be another grapefruit about 4,000 kilometers away. That's roughly the distance from London to Cairo. 2 grapefruits, separated by the width of a continent, each surrounded by a few barely visible specks of dust. That's our solar neighborhood. That's how empty interstellar space really is. That's the thing about interstellar distances. They are not just large. They are prohibitively, almost insultingly large. The gaps between stars are so vast that they make the enormous distances within our solar system seem like rounding errors. And yet, the stars look so close together in the night sky. You can cover the distance between 2 stars with your thumb held at arm's length. But that visual closeness is an illusion created by the immensity of the distances involved. The stars are scattered across three-dimensional space at distances so great that our sense of perspective collapses entirely. Proxima Centauri is part of a triple star system called Alpha Centauri. The other two stars, Alpha Centauri A and Alpha Centauri B, are a binary pair that orbit each other at a distance of about 23 astronomical units, roughly the distance from the Sun to Uranus. They are Sun-like stars, the kind of stars that might host habitable planets. In fact, in 2016, astronomers discovered a planet orbiting Proxima Centauri in its habitable zone, the region where temperatures might allow liquid water to exist on the surface. The planet is called Proxima Centauri b, and it's roughly Earth-sized. Whether it has an atmosphere, water, or any conditions hospitable to life remains unknown. But its discovery sent a thrill through the scientific community. The nearest star to us has a potentially habitable planet. Let's continue outward. Within about 10 light-years of the Sun, there are about a dozen known star systems. Most are red dwarfs, small and dim, invisible to the naked eye. Within 20 light-years, there are about 100 known star systems. Within 50 light-years, the number grows to several hundred. But these are still our immediate neighbors, the stars in our tiny cosmic backyard. To truly grasp the distances between stars, it helps to think about how we measure them. Astronomers use a technique called parallax. As the Earth orbits the Sun, our vantage point shifts by about 300 million kilometers over 6 months. Nearby stars appear to shift slightly against the background of more distant stars, just as a nearby lamppost seems to move against distant mountains when you shift your head from side to side. By measuring this tiny angular shift, astronomers can calculate the star's distance using simple trigonometry. Parallax works well for nearby stars out to a few thousand light-years. Beyond that, the angular shifts become too small to measure accurately, even with the most precise instruments. For more distant objects, astronomers rely on other methods, collectively known as the cosmic distance ladder. Standard candles, objects of known luminosity, are particularly useful. If you know how bright something truly is, you can determine how far away it is by measuring how bright it appears. Cepheid variable stars, whose luminosity is related to their pulsation period, were the first reliable standard candles and were used by Edwin Hubble to prove that other galaxies existed beyond the Milky Way. Type Ia supernovae, exploding white dwarf stars that reach a characteristic peak brightness, are used to measure distances across billions of light-years. It was these supernovae that led to the discovery of the accelerating expansion of the universe in 1998, one of the most important discoveries in the history of science. As we move outward, the stars we encounter become more diverse. Not just red dwarfs, but orange dwarfs, yellow dwarfs, like our Sun, white dwarfs, and the occasional giant or supergiant. Some are solitary, drifting alone through space. Others are in binary or multiple star systems, 2 or 3 or more stars locked in gravitational embrace, orbiting a common center of mass. Some are surrounded by planetary systems. Others seem to have none. The variety is enormous, but the pattern is always the same. Vast, empty space, punctuated by tiny, isolated points of light, separated by distances that dwarf everything within them, and many of those stars have planets. This is one of the great discoveries of the past 3 decades. Since the first confirmed detection of an exoplanet, a planet orbiting another star, in 1992, astronomers have found more than 5,600 confirmed exoplanets, with thousands more candidates awaiting confirmation. The Kepler Space Telescope, which operated from 2009 to 2018, revolutionized the field by monitoring the brightness of more than 150,000 stars simultaneously, looking for the tiny dips in brightness caused when a planet passes in front of its star. Kepler discovered more than 2,600 exoplanets and revealed that planets are extraordinarily common. Statistical analyses of Kepler's data suggest that there are, on average, at least 1 to 2 planets per star in the Milky Way. That means there are hundreds of billions of planets in our galaxy alone. The diversity of exoplanets is astonishing. Hot Jupiters, gas giants that orbit their stars in just a few days, scorched to temperatures of thousands of degrees. Super-Earths, rocky planets larger than Earth but smaller than Neptune, a category that has no equivalent in our solar system. Mini-Neptunes, worlds wrapped in thick atmospheres of hydrogen and helium. And potentially, somewhere out there, Earth-like planets, rocky worlds in the habitable zones of sun-like stars, with liquid water on their surfaces and perhaps, just perhaps, life. The James Webb Space Telescope is beginning to study the atmospheres of some of these exoplanets, looking for signatures of water vapor, carbon dioxide, methane, and other molecules that might indicate habitable conditions or even biological activity. We are, for the first time in history, developing the ability to detect signs of life on other worlds. Whether we will find them remains to be seen. But the search itself is one of the most profound endeavors our species has ever undertaken. At about 25,000 light-years from our current position, if we travel toward the center of the Milky Way, we would approach the galactic core. But before we go there, let's consider the structure of the galaxy we live in. The Milky Way is a barred spiral galaxy, about 100,000 to 180,000 light-years in diameter and about 2,000 light-years thick in the disk, though recent measurements suggest a range of thicknesses depending on the stellar population. It contains an estimated 100 to 400 billion stars, along with vast quantities of gas, dust, dark matter, and at least as many planets as stars, probably more. Our Sun is located in one of the galaxy's spiral arms, the Orion Arm, about 26,000 light-years from the galactic center. We're not at the edge and not at the center, but somewhere in the middle suburbs. If you could see the Milky Way from the outside, it would look like a vast flat disk of stars, gas and dust, with a bright central bulge and sweeping spiral arms curving outward from a central bar. The spiral arms are regions of higher density, where gas is compressed and new stars are born. They glow with the blue-white light of hot, massive, short-lived stars, the kind that burn fast and die young in spectacular supernovae. Between the arms, the stars are older, quieter, redder. The disk is embedded in a larger, roughly spherical halo of old stars, globular clusters, and dark matter that extends far beyond the visible disk. Globular clusters are among the oldest objects in the Milky Way. These dense, spherical collections of hundreds of thousands to millions of stars orbit the galactic center in the halo, far above and below the disk. Many of them are 12 to 13 billion years old, nearly as old as the universe itself. They formed in the earliest stages of the Milky Way's assembly, and they carry the chemical fingerprints of that ancient era, with very low abundances of heavy elements. They are fossils, relics of a time when the galaxy was young and the universe was still in its infancy. At the very center of the Milky Way lies a supermassive black hole called Sagittarius, a star. It has a mass of about 4 million times that of our Sun, compressed into a region smaller than Mercury's orbit. Despite its enormous mass, Sagittarius, a star, is relatively quiet compared to the supermassive black holes in some other galaxies. It's not actively consuming large quantities of matter, so it doesn't produce the brilliant jets and radiation that characterize active galactic nuclei. But it's there, sitting at the gravitational center of the galaxy, holding everything in its grip. Stars near the galactic center orbit it at tremendous speeds, some completing their orbits in just a few years, providing direct evidence of the black hole's presence and mass. In 2020, the Nobel Prize in Physics was awarded in part to Andrea Ghez and Reinhard Genzel for their decades of work tracking stars orbiting Sagittarius A star. By observing these stars with adaptive optics on large ground-based telescopes, they were able to determine the mass and location of the black hole with extraordinary precision, providing the most convincing evidence yet that supermassive black holes are real. The region around the galactic center is dense, chaotic, and beautiful. Stars are packed thousands of times more closely than in our neighborhood. Vast clouds of gas and dust glow in infrared and radio wavelengths, heated by the intense radiation from millions of stars. Star formation is active. Supernova remnants pepper the region. And, threading through it all, magnetic fields, cosmic rays, and the gravitational influence of the central black hole create a dynamic, turbulent environment unlike anything in the quieter outer regions of the galaxy. But we can't see the galactic center with our eyes. Between us and it lies about 26,000 light-years of gas and dust, which absorbs visible light and hides the center from view. When you look at the Milky Way on a dark summer night, that bright, dense band of light stretching across the sky, you're looking toward the center of the galaxy, but you're seeing only the nearest stars and dust clouds. The center itself is hidden behind a veil of interstellar material. It was only with the development of radio and infrared telescopes, which can see through the dust, that astronomers were able to study the galactic center in detail. Let's continue our journey outward, beyond the Milky Way's disk, into the vast emptiness of intergalactic space. But first, let's appreciate what we're leaving behind. The Milky Way is enormous. Light takes about 100,000 years to cross it. If you were to shrink the Milky Way to the size of a football field, the solar system would be smaller than a grain of sand, and within this grain of sand lies everything we've ever known. Every human being who has ever lived, every civilization that has ever risen and fallen, every ocean and mountain and forest, all contained within a space so small that, on the scale of the galaxy, it's essentially invisible. Now let's step outside. The nearest large galaxy to the Milky Way is the Andromeda Galaxy, also known as Messier 31 or M31. It's about 2.5 million light-years away. That means the light we see from Andromeda tonight left that galaxy 2.5 million years ago, when our ancestors were just beginning to use stone tools on the plains of Africa. Homo habilis, one of the earliest members of the genus Homo, was walking the Earth when the light that reaches us tonight from Andromeda began its journey. When you look at Andromeda, and you can see it with the naked eye on a clear, dark night, a faint, fuzzy smudge in the constellation Andromeda, you're looking 2.5 million years into the past. And here is something worth contemplating. The Andromeda Galaxy is the most distant object you can see with the naked eye. Everything else you see in the night sky without a telescope, every star, every planet, every nebula visible to the unaided eye, is within the Milky Way. But Andromeda is out there, a separate galaxy, a separate island of stars, visible across a gulf of 2.5 million light-years. The fact that you can see it at all is a testament to its size and luminosity. It contains about 1 trillion stars. Andromeda is a spiral galaxy, similar in size and structure to the Milky Way, though probably somewhat larger. It has its own supermassive black hole at its center, its own spiral arms, its own population of globular clusters, and its own retinue of satellite galaxies, smaller galaxies orbiting around it like moons around a planet. The Milky Way and Andromeda are on a collision course. They're approaching each other at about 110 kilometers per second, drawn together by mutual gravity. In about 4 to 5 billion years, they'll collide. The merger will take hundreds of millions of years, a slow-motion dance of gravitational tides and stellar streams. Stars themselves won't collide, they're too widely spaced, but the shapes of both galaxies will be utterly transformed. New bursts of star formation will be triggered by the compression of gas clouds. The spiral arms will be torn apart and reformed. And eventually, after perhaps 1 billion years, the two galaxies will settle into a single, larger galaxy, probably an elliptical galaxy, sometimes nicknamed Milkdromeda. But the Milky Way and Andromeda are not alone. They're part of a collection of galaxies called the Local Group, a gravitationally bound cluster of about 80 known galaxies spread across roughly 10 million light-years of space. The Local Group is dominated by two large spirals, the Milky Way and Andromeda, along with a third, smaller spiral, the Triangulum Galaxy, about 2.7 million light-years away. The rest are mostly small, faint dwarf galaxies, many of them satellites of the two big spirals. The Large and Small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches of light, are two of the Milky Way's satellite galaxies. They are irregular dwarf galaxies, about 160,000 and 200,000 light-years away respectively, close enough to be gravitationally interacting with the Milky Way. The Large Magellanic Cloud contains the Tarantula Nebula, one of the most active star-forming regions in the Local Group, a vast cloud of gas and dust where massive, brilliant stars are being born at a prodigious rate. The Local Group, in turn, is part of a larger structure. The Virgo supercluster, a collection of about 100 galaxy groups and clusters spread across roughly 110 million light-years. The Virgo supercluster is centered on the Virgo cluster, a dense concentration of about 1,500 galaxies located about 54 million light-years from us. The Virgo cluster is the gravitational heart of our supercluster, and its gravity influences the motion of every galaxy in the neighborhood, including our own. But even the Virgo supercluster is not the largest structure we belong to. In 2014, astronomers defined a still larger structure called Laniakea, a Hawaiian word meaning immense heaven. Laniakea is a supercluster of superclusters, a vast basin of gravitational attraction, spanning about 520 million light-years and containing roughly 100,000 galaxies. The Milky Way, the Local Group, the Virgo supercluster, all are part of Laniakea. And Laniakea itself is just one of many superclusters in the observable universe. Let's pause again and take a breath. We've traveled from the surface of the Earth, through the solar system, past the nearest stars, through the Milky Way, across 2.5 million light-years to Andromeda, and out to the scale of superclusters spanning hundreds of millions of light-years. And we're still not at the edge. We're still, in a sense, in our local neighborhood. The observable universe is much, much larger. But before we continue outward, let's talk about what we mean by the observable universe, because it's a concept that's often misunderstood, and getting it right is essential to understanding what the edge means. The observable universe is not the whole universe. It's the part of the universe that we can, in principle, see. The part from which light has had time to reach us since the Big Bang, about 13.8 billion years ago. Light travels at a finite speed, about 300,000 kilometers per second. And since the universe has a finite age, there's a maximum distance from which light could have traveled to reach us. That distance defines the boundary of the observable universe. Now, you might think that the radius of the observable universe should be 13.8 billion light-years, since the universe is 13.8 billion years old. But it's not. It's about 46.5 billion light-years. The reason for this discrepancy is the expansion of space. While the light has been traveling toward us, the space it has been traveling through has been stretching. The source of the light, wherever it was 13.8 billion years ago, has been carried farther away by the expansion of space. So by the time the light reaches us, the object that emitted it is much farther away than 13.8 billion light-years. It's about 46.5 billion light-years away, and the total diameter of the observable universe, from one edge to the other is about 93 billion light-years. This is a staggering number, 93 billion light-years across. To even begin to appreciate what this means, consider that the Milky Way, our entire galaxy, containing hundreds of billions of stars, is about 100,000 light-years across. The observable universe is roughly 930,000 times wider than the Milky Way. And within this volume, astronomers estimate there are about 2 trillion galaxies. 2 trillion. That's 2,000,000 galaxies, each containing billions or trillions of stars. The total number of stars in the observable universe is estimated at roughly 200 sextillion. That's a 2 followed by 23 zeros. More stars than there are grains of sand on every beach on Earth, and yet most of the observable universe is empty. Staggeringly, overwhelmingly empty. The average density of matter in the universe is about 5 atoms per cubic meter. 5 atoms in a space the size of a large refrigerator. If you could take all the matter in the observable universe and spread it out evenly, it would be a near-perfect vacuum, far emptier than any vacuum we can create in a laboratory. The vast distances between galaxies, between galaxy clusters, between the great cosmic structures, are filled with almost nothing at all. Just a scattering of hydrogen atoms, a few photons, and the mysterious energy of the vacuum itself. Let's continue our journey outward. We've reached the scale of superclusters, structures spanning hundreds of millions of light-years. Now let's zoom out further and look at the largest structures in the observable universe. At the largest scales, the distribution of galaxies in the universe is not uniform. It's organized into a vast three-dimensional pattern called the cosmic web. The cosmic web is a network of filaments, walls and nodes separated by enormous voids. The filaments are long, thin concentrations of galaxies and dark matter, stretching across hundreds of millions of light-years. The walls are flat, sheet-like structures where filaments intersect. The nodes are the densest concentrations, the galaxy clusters and superclusters that sit at the intersections of multiple filaments. And the voids are the vast, nearly empty spaces between the filaments, regions spanning hundreds of millions of light-years that contain very few galaxies. This structure didn't arise by chance. It's the result of 13.8 billion years of gravitational evolution, starting from tiny fluctuations in the density of matter in the early universe. In the first moments after the Big Bang, the universe was almost perfectly uniform. But it wasn't quite perfect. There were tiny variations in density, fluctuations of about 1 part in 100,000, imprinted by quantum processes during the earliest moments of cosmic history. Over billions of years, gravity amplified these tiny fluctuations. Regions that were slightly denser than average attracted more matter, growing denser still. Regions that were slightly less dense lost matter, becoming emptier. Over time, matter flowed from the voids into the filaments, from the filaments into the nodes, building up the cosmic web we see today. The cosmic web is the largest pattern in the known universe. It extends across the entire observable universe, a structure so vast that no single telescope has ever captured it in a single image. We know about it because of large-scale galaxy surveys, projects that have mapped the positions of millions of galaxies in 3 dimensions, revealing the filaments and voids that thread through space like the strands of an impossibly vast spider's web. Some of the voids in the cosmic web are enormous. The Bootes void, discovered in 1981, is a roughly spherical region about 330 million light-years in diameter that contains very few galaxies. To travel across it at the speed of light would take 330 million years, and during that entire journey, you would see almost nothing. Just empty space, stretching in every direction, with only a handful of galaxies scattered across the entire volume. It is one of the loneliest places in the known universe. The KBC void, identified more recently, may be even larger, spanning about 2 billion light-years. Some researchers have proposed that our own local group sits near the center of this void, which could partially explain a persistent tension in measurements of the universe's expansion rate. Whether this is true remains debated, but the existence of such enormous empty regions is itself a remarkable feature of the cosmos. Let's zoom out one more level and consider the universe on its largest scale. At this scale, the cosmic web itself fades into uniformity. One of the fundamental principles of modern cosmology, known as the cosmological principle, states that on sufficiently large scales, the universe is homogeneous and isotropic. That means it looks the same everywhere and in every direction. There's no center, no edge, no special location. Every point in the universe is, on average, the same as every other point. Now let's talk about what happens as we approach the edge of the observable universe. Because the edge is not a wall. It's not a boundary in space. It's a boundary in time. As we look deeper into space, we look further back in time. A galaxy 1 billion light-years away appears as it was 1 billion years ago. A galaxy 10 billion light-years away appears as it was 10 billion years ago. As we push outward, we see galaxies as they were when they were younger. At 10 billion light-years, we see galaxies in their adolescence, still forming, still growing, still assembling from mergers with smaller galaxies. At 12 billion light-years, we see galaxies in their infancy, irregular, chaotic, blazing with the light of newborn stars. At 13 billion light-years, we see the faintest, most distant galaxies ever observed, tiny smudges of light that represent the earliest galaxies in the universe, forming just a few 100 million years after the Big Bang. One of the most iconic images in the history of astronomy is the Hubble Deep Field. In 1995, astronomers pointed the Hubble Space Telescope at a tiny, apparently empty patch of sky, a region so small you could cover it with a grain of sand held at arm's length. They exposed the camera for 10 consecutive days, collecting every photon of light from that tiny area. The result was astonishing. The image revealed about 3,000 galaxies, stretching back to when the universe was less than 1 billion years old. A grain of sand's worth of sky, and it contained thousands of galaxies. The implication was staggering. If a random tiny patch of sky contains this many galaxies, then the total number of galaxies in the observable universe must be enormous. This was one of the first direct indications that the universe contains hundreds of billions, perhaps trillions of galaxies. Subsequent deep field images, including the Hubble Ultra Deep Field and the James Webb Space Telescope's deep field images, have pushed even deeper, revealing galaxies at even greater distances and earlier times. The James Webb Space Telescope, launched in 2021, has pushed our view deeper into cosmic history than ever before. It has detected galaxies that formed when the universe was only 300 to 400 million years old. These are among the most distant objects ever observed, and they appear as they were more than 13 billion years ago. They are tiny, faint, and irregular, nothing like the grand spirals and ellipticals we see nearby. They are the building blocks from which all later galaxies were assembled, the cosmic seeds from which the structure of the universe grew. Some of these early galaxies have surprised astronomers. They are brighter, more massive, and more mature than theoretical models predicted. Some appear to have already formed billions of stars by the time the universe was only a few 100 million years old, which challenges our understanding of how quickly galaxies can assemble. These observations are still being analyzed and debated, and they may require revisions to our theories of galaxy formation. The early universe, it seems, was even more dynamic and productive than we thought. But we can see even further back than the first galaxies. If we push our view to the very edge of the observable universe, we encounter something extraordinary: the cosmic microwave background. The cosmic microwave background, or CMB, is the oldest light in the universe. It was emitted about 380,000 years after the Big Bang, at a moment called recombination, when the universe cooled enough for hydrogen atoms to form for the first time. Before recombination, the universe was a hot, dense plasma of free protons, electrons, and photons. The photons couldn't travel far without being scattered by the free electrons, so the universe was opaque. It was like being inside a fog. But when the temperature dropped to about 3000 Kelvin, the electrons combined with protons to form neutral hydrogen atoms, and the photons were suddenly free. They began to travel through space, unimpeded, and they've been traveling ever since for 13.8 billion years. Those photons are the CMB. They fill the universe in every direction, a faint, uniform glow that pervades all of space. When they were emitted, they were visible light, orange-red, like the glow of a hot iron. But the expansion of space has stretched their wavelengths by a factor of about 1,100, shifting them from visible light into the microwave part of the spectrum. Today, the CMB has a temperature of about 2.725 Kelvin, just a few degrees above absolute zero. It is the coldest natural thing in the universe, and it is everywhere. The CMB was first detected accidentally in 1965 by Arno Penzias and Robert Wilson, two radio astronomers at Bell Labs in New Jersey. They were testing a sensitive microwave antenna and found a persistent background noise that they couldn't eliminate. It came from every direction. It didn't change with the time of day or the season. It was constant, uniform, and inexplicable, until they learned that cosmologists at nearby Princeton University had predicted exactly such a signal as the afterglow of the Big Bang. Penzias and Wilson had stumbled upon one of the most important discoveries in the history of science. They were awarded the Nobel Prize in 1978. The CMB is not perfectly uniform. It has tiny variations in temperature, fluctuations of about 1 part in 100,000. These fluctuations are the imprint of the density variations in the early universe, the same variations that would eventually grow, under the influence of gravity, into the galaxies, clusters, and cosmic web we see today. The pattern of fluctuations in the CMB is a snapshot of the universe at the age of 380,000 years, the earliest image we can ever obtain using light. It's the baby picture of the cosmos. These fluctuations have been mapped with extraordinary precision, first by the COBE satellite in the early 1990s, then by the WMAP satellite in the 2000s, and most recently by the Planck satellite, which completed its observations in 2013. The Planck data revealed the fluctuations in exquisite detail, providing measurements of the age, composition, and geometry of the universe with percent-level accuracy. The Planck results confirm that the universe is 13.8 billion years old, that it's composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy, and that its geometry is very close to flat. These numbers form the foundation of the modern cosmological model, and they have been confirmed by multiple independent lines of evidence. The CMB represents the edge of the observable universe, not because there's nothing beyond it, but because we can't see beyond it. Before recombination, the universe was opaque. Any light emitted before that time was scattered and absorbed, erased by the hot plasma. The CMB is a wall of light, the last scattering surface, beyond which we cannot see using electromagnetic radiation. It's the cosmic horizon, the boundary of our observable volume, and it surrounds us in every direction, a sphere of ancient light with us at the center. But being at the center of the observable universe doesn't mean we're at the center of the universe. Every observer, anywhere in the universe, would see themselves at the center of their own observable volume. It's like standing in a thick fog. You can see a certain distance in every direction, and you appear to be at the center of a circle of visibility. But someone standing a kilometer away would also see themselves at the center of their own circle. Neither of you is at the true center. There is no true center. The fog extends in every direction, and the only thing that limits your view is how far you can see. This is a profound and somewhat unsettling fact. There are regions of the universe that we can never observe, never contact, never know about. The observable universe, vast as it is, with its 2 trillion galaxies and 200 sextillion stars, is just a bubble within a much larger cosmos. How much larger? We don't know. The universe might be finite or infinite. Current observations are consistent with both possibilities. If it's finite, it might be many times larger than the observable volume. Perhaps trillions of times, perhaps incomprehensibly more. If it's infinite, then the observable universe is an infinitesimally small patch in an endless expanse. Either way, what we can see is not all there is. It may be the tiniest fraction of all there is. Let's sit with that thought for a moment. The observable universe, this sphere 93 billion light-years across, containing more galaxies than there are grains of sand on Earth, more stars than any number we've ever needed in everyday life, is potentially just a tiny bubble in something much, much larger. A bubble whose contents, whose galaxies and stars and planets and perhaps civilizations are just a minuscule sample of what exists beyond our view. And yet this is all we have. This is our cosmos, the part we can see, the part we can study, the part we can know. And what we've found within it is extraordinary. Let's talk about some of the remarkable things that exist within the observable universe. The objects and phenomena that astronomers have discovered as they've pushed their telescopes deeper and deeper into space and time. Let's start with quasars. Quasars are among the most luminous objects in the observable universe. They are the brilliant cores of distant galaxies powered by supermassive black holes that are actively consuming enormous quantities of matter. As matter spirals into the black hole, it forms a superheated accretion disk that radiates energy across the electromagnetic spectrum, from radio waves to X-rays. The energy output can be stupendous. A single quasar can outshine its entire host galaxy by a factor of 100 or more, blazing with the luminosity of trillions of suns. The most distant quasar currently known is about 13.1 billion light-years away, meaning we see it as it was when the universe was only about 700 million years old. The supermassive black hole at its center has a mass of about 1.6 billion solar masses, an astonishing size for such an early epoch. How such massive black holes formed so quickly after the Big Bang is one of the outstanding puzzles of modern astrophysics. Let's also consider galaxy clusters, the largest gravitationally bound structures in the universe. A galaxy cluster can contain hundreds or thousands of galaxies, bound together by their mutual gravity and embedded in a vast halo of hot gas and dark matter. The hot gas, called the intracluster medium, has temperatures of tens of millions of degrees, so hot that it emits X-rays. This gas is not part of any individual galaxy. It fills the space between the galaxies, a diffuse, superheated atmosphere that pervades the entire cluster. Gravitational lensing is one of the most beautiful and useful phenomena in observational astronomy. When light from a distant galaxy passes near a massive object, like a galaxy cluster, the gravity of the cluster bends the light, distorting and magnifying the image of the background galaxy. In some cases, the distortion produces multiple images of the same galaxy, or stretches it into long, thin arcs called Einstein rings. In other cases, the magnification allows astronomers to see galaxies that would otherwise be too faint and too distant to detect, using the cluster as a natural telescope. The James Webb Space Telescope has made spectacular use of gravitational lensing. By pointing at massive galaxy clusters and using their gravity as a lens, JWST has detected some of the most distant galaxies ever observed, galaxies that formed in the first few 100 million years after the Big Bang. These galaxies are so faint that without the magnification of the lensing cluster, they would be completely invisible. Gravitational lensing has opened a window into the earliest epochs of cosmic history, allowing us to see the first steps in the formation of the universe's structure. Now let's push our view to the very edge of the observable universe and consider what lies at and beyond the cosmic microwave background. The universe existed before the CMB. There were events before recombination, during the first 380,000 years, that shaped the universe we see today. We just can't observe them directly with light. In the first fractions of a second after the Big Bang, the universe underwent a period of extraordinarily rapid expansion called inflation. During inflation, the universe expanded by a factor of at least 10 to the 26th in a tiny fraction of a second, doubling in size roughly every 10 to the minus 37th of a second. This expansion smoothed out any irregularities in the fabric of space-time, producing the nearly uniform universe we observe today. It also amplified tiny quantum fluctuations, random variations in the energy density of the inflating field, into the seeds that would eventually grow into the cosmic web. After inflation ended, the universe was filled with an incredibly hot, dense plasma of elementary particles, quarks, leptons, and the force-carrying particles that mediate the fundamental interactions. As the universe expanded and cooled, quarks combined into protons and neutrons. Within the first few minutes, protons and neutrons fused into the nuclei of the lightest elements, hydrogen, helium, and traces of lithium and beryllium. This process is called Big Bang nucleosynthesis, and the predicted abundances of these light elements match the observed abundances with remarkable precision. It is one of the strongest pieces of evidence for the Big Bang theory. For the next 380,000 years, the universe was a hot, opaque plasma. Then, as we described, the universe cooled enough for atoms to form, the photons were released, and the CMB was born. After recombination, the universe entered a period sometimes called the Dark Ages. There were no stars, no galaxies, no sources of light. Just a vast, expanding sea of neutral hydrogen and helium gas, cooling slowly in the darkness. The CMB photons continued to travel through this gas, redshifting as the universe expanded. And gravity continued its slow work, pulling matter into the tiny density peaks, seeded by inflation, building the foundations of the cosmic web. The Dark Ages lasted for about 100 to 200 million years. Then, in the densest regions of the cosmic web, the first stars began to form. These first-generation stars, sometimes called population 3 stars, were unlike any stars that exist today. They were made entirely of hydrogen and helium, with no heavier elements. Without heavy elements, the gas cooled less efficiently, and the first stars may have been extremely massive, perhaps hundreds of times the mass of our Sun. They would have been hot, blue, and short-lived, burning through their fuel in just a few million years before exploding as supernovae or collapsing into black holes. No population 3 star has ever been directly observed. They are too distant and too ancient for even our best telescopes, but their signatures may be detectable in the chemical composition of the oldest surviving stars in the Milky Way's halo, second-generation stars that formed from gas enriched by the first supernovae. These ancient stars, some of which have been found with extremely low abundances of heavy elements, may carry the chemical fingerprints of the very first generation of stars. These first stars were transformative. Their light ended the cosmic dark ages, ionizing the hydrogen gas around them and creating bubbles of transparency in the otherwise opaque intergalactic medium. As more stars formed and more bubbles grew, the bubbles began to overlap, and the intergalactic medium became increasingly ionized. This process, called reionization, transformed the universe from opaque to transparent. Reionization was probably complete by about 1 billion years after the Big Bang. The first stars also produced the first heavy elements. When they exploded as supernovae, they scattered carbon, oxygen, nitrogen, silicon, iron, and other elements into the surrounding gas. These elements were incorporated into the next generation of stars, enriching them with the chemical complexity needed to form rocky planets and organic molecules. Every heavy element in the universe, every atom of carbon in your body, every atom of oxygen in your lungs, every atom of iron in your blood was produced in a star that lived and died before the Earth existed. You are made of stellar debris. Stardust, shaped by gravity and chemistry into a being that can contemplate its own origins. The first galaxies formed from the merger of smaller protogalactic fragments, clumps of gas and dark matter, that fell together under gravity. Over billions of years, they grew through mergers, accreting smaller galaxies and gas, building up mass and complexity. By about 3 to 4 billion years after the Big Bang, the universe was in full bloom. Galaxies were forming, merging, and evolving at a rapid pace. Star formation rates were at their peak. The cosmic web was taking shape. The stage was being set for the universe we see today. Over the next 10 billion years, the pace gradually slowed. Star formation rates declined as galaxies used up their gas supplies. Galaxies settled into more stable configurations, and the expansion of the universe began to accelerate, driven by dark energy. Dark energy is perhaps the deepest mystery in modern physics. We know it exists because of its effect on the expansion of the universe. In 1998, two teams of astronomers studying distant type Ia supernovae discovered that the expansion of the universe is not slowing down, as gravity would suggest, but speeding up. Something is pushing the universe apart, counteracting gravity on the largest scales. That something is dark energy. We don't know what dark energy is. It might be a property of space itself, a cosmological constant, the energy of the vacuum. It might be a dynamic field that changes over time. It might be something else entirely, something we haven't yet imagined. But its effects are clear. It dominates the energy budget of the universe, comprising about 68% of the total mass energy content. It drives the accelerating expansion, and it will determine the ultimate fate of the cosmos. In a universe dominated by dark energy, the expansion will continue to accelerate forever. Distant galaxies will be carried farther and farther away, their light redshifting into invisibility. Over trillions of years, the galaxies beyond our local group will fade from view, carried beyond the cosmic horizon by the relentless expansion of space. Any civilization living in the far future would see only the galaxies of the local group, a small cluster in an otherwise empty sky. They would have no way of knowing that the universe once contained trillions of galaxies, that the sky was once filled with light. Now, let's consider some of the most extreme and exotic objects that exist within the observable universe. Neutron stars are among the densest objects in the cosmos. They form when massive stars explode as supernovae and their cores collapse to extraordinary densities. A neutron star packs about 1.4 to 2 times the mass of the Sun into a sphere only about 20 kilometers across. A teaspoon of neutron star material would weigh about 1 billion tons. The gravity at the surface is about 200 billion times stronger than Earth's gravity. And neutron stars can spin incredibly fast, some rotating hundreds of times per second, emitting beams of radio waves that sweep across space like lighthouse beams. These are pulsars, and they are among the most precise natural clocks in the universe. The regularity of their pulses rivals atomic clocks and can be used to detect gravitational waves, test general relativity, and even navigate spacecraft. Some neutron stars are magnetars, objects with magnetic fields 1,000 trillion times stronger than Earth's. These are the most powerful magnets in the universe. A magnetar's magnetic field is so intense that it would be lethal at a distance of 1,000 kilometers, disrupting the electron clouds of atoms and destroying the molecular bonds in living tissue. Magnetars occasionally produce enormous flares, releasing more energy in a fraction of a second than the Sun emits in 100,000 years. One such flare from a magnetar in our own galaxy was detected in 2004. Despite being about 50,000 light-years away, the flare was powerful enough to measurably affect the Earth's ionosphere. Then there are fast radio bursts, one of the newest and most mysterious phenomena in astronomy. First detected in 2007, fast radio bursts are brief, intense pulses of radio emission lasting just milliseconds, but releasing as much energy as the Sun produces in a day. They come from distant galaxies, billions of light-years away. Some repeat, most don't. The leading explanation is that they are produced by magnetars, but the exact mechanism remains unclear. They are one of the hottest topics in modern astronomy, and new detections are being made almost daily by radio telescopes around the world. Black holes, the ultimate endpoints of gravitational collapse. In 2019, the Event Horizon Telescope, a global network of radio telescopes linked together to form an Earth-sized virtual dish, captured the first direct image of a black hole's shadow. The black hole was at the center of M87, a giant elliptical galaxy in the Virgo cluster, about 55 million light-years away. The image showed a bright ring of superheated gas orbiting the black hole, surrounding a dark central shadow, the event horizon. In 2022, the same team released an image of Sagittarius A star, our own galaxy's central black hole. These images were milestones in the history of astronomy, the first visual confirmation of objects that had been predicted by Einstein's general relativity more than a century earlier. Gravitational waves, ripples in the fabric of space-time produced by accelerating massive objects, are another prediction of general relativity confirmed in recent years. In 2015, the LIGO Observatory detected gravitational waves for the first time, from the merger of two stellar black holes about 1.3 billion light-years away. The signal was extraordinarily subtle. The gravitational waves stretched and compressed the LIGO detector's 4-kilometer-long arms by a distance smaller than 1/10,000th the diameter of a proton. That this signal was detected at all is a testament to the extraordinary precision of the instrument and the dedication of the scientists who built it. Since then, LIGO and its partner observatory Virgo have detected dozens of gravitational wave events, opening an entirely new window on the universe. In 2017, LIGO and Virgo detected gravitational waves from the merger of two neutron stars, an event called GW170817. This time, the merger also produced light, a burst of gamma rays detected just 1.7 seconds after the gravitational wave signal, followed by a fading glow visible across the electromagnetic spectrum for weeks. This was the first time an astronomical event was observed with both gravitational waves and light, inaugurating the era of multi-messenger astronomy. The observations confirm that neutron star mergers produce heavy elements like gold, platinum, and uranium through a process called rapid neutron capture, or the R process. Much of the gold on Earth was probably produced in neutron star mergers billions of years ago and delivered to the forming solar system by the gas cloud, from which the Sun and planets condensed. Let's also talk about dark matter. Dark matter makes up about 27% of the total mass energy content of the universe, roughly 5 times more than ordinary baryonic matter. But dark matter doesn't emit light, absorb light, or interact with electromagnetic radiation in any way. We know it exists because of its gravitational effects. Galaxies rotate faster than they should based on the visible matter they contain, implying that they're embedded in vast halos of invisible matter. Galaxy clusters contain far more mass than their visible galaxies and gas can account for. And the cosmic microwave background shows patterns that can only be explained if dark matter exists. Despite decades of effort, the nature of dark matter remains one of the greatest unsolved problems in physics. Together with dark energy, it makes up about 95% of the total mass energy content of the universe. Ordinary matter, the atoms that make up stars and planets and people, accounts for only about 5%. We are, in a very real sense, a tiny minority in a universe dominated by substances we don't understand. The cosmos is made mostly of mystery. The geometry of the universe is determined by its total energy density. Einstein's general relativity tells us that the geometry of space-time is shaped by its contents. Observations have determined that the universe is very, very close to flat, a result naturally explained by inflation, which stretched any initial curvature to near zero. A flat universe can be either finite or infinite. The question of whether the universe is finite or infinite is one of the deepest questions in cosmology. We may never be able to answer it definitively because our observations are limited to the observable universe, a finite bubble within a potentially infinite expanse. Whatever lies beyond the edge of our observable volume is, and may forever remain, unknown. Now, as we approach the final stages of our journey, let's reflect on what it means to look at the night sky. When you look up at the stars, you're not seeing the universe as it is right now. You're seeing it as it was. The light from each star left that star at some point in the past and has been traveling through space ever since. The nearest stars a few light years away appear as they were a few years ago. The stars you can see with the naked eye, most of which are within a few hundred light years, appear as they were a few hundred years ago. The Andromeda Galaxy appears as it was 2.5 million years ago, and the most distant galaxies visible to our telescopes appear as they were more than 13 billion years ago. The night sky is a time machine. Every point of light is a window into the past, and the deeper you look, the further back you go. The observable universe is not a snapshot of the cosmos at a single moment. It's a layered panorama of cosmic history, with the nearest objects showing the present and the most distant objects showing the ancient past. This means that the universe we observe is not a place in the usual sense. It's a history, a record of everything that has happened within our light cone, the region of space-time from which light has had time to reach us, and that history is finite. It begins with the Big Bang, 13.8 billion years ago, and it extends outward in all directions to the cosmic microwave background. Beyond that, we cannot see, but there may be other ways to peer deeper. Gravitational waves are not impeded by plasma. They pass through everything. In principle, gravitational waves from the very earliest moments of the universe, from inflation itself, might still be reverberating through space, imprinted on the CMB or detectable by future gravitational wave observatories. If we could detect these primordial gravitational waves, they would carry information about the universe before recombination, before nucleosynthesis, before even the first second. They would be messages from the very beginning of time. Neutrinos offer another possibility. The universe is filled with a cosmic neutrino background, produced about 1 second after the Big Bang. These neutrinos carry information about an even earlier epoch than the CMB. Detecting them directly is extraordinarily difficult, but future experiments may be able to detect the cosmic neutrino background, opening a new window on the first seconds of cosmic history. And then there's the question of what came before the Big Bang, or whether that question even makes sense. In the standard cosmological model, the Big Bang is the beginning of time itself. But some cosmological models suggest that the Big Bang was not the absolute beginning, but rather a transition from a previous state. In eternal inflation models, our Big Bang was just one of an infinite number of Big Bangs, each producing a separate bubble universe in a vast, ever-expanding multiverse. In cyclic models, the Big Bang was preceded by a big crunch, the collapse of a previous universe. These are speculative ideas at the very frontier of theoretical physics, but they remind us that the observable universe, vast as it is, may not be all there is. Let's take a breath now. A slow, deep breath. We've traveled a long way tonight, from the surface of the Earth, through the solar system, past the nearest stars, through the Milky Way, across millions of light years to neighboring galaxies, through the cosmic web of filaments and voids, past quasars and galaxy clusters, all the way back to the cosmic microwave background, the oldest light in the universe. We've covered 46.5 billion light-years, the radius of the observable universe, and we've spanned 13.8 billion years of cosmic history. And what have we found? We've found a universe of staggering size and beauty, a universe filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, a universe woven together by gravity and expanded by dark energy. A universe where matter clusters into filaments and walls, separated by enormous voids. A universe where black holes warp space-time and neutron stars spin hundreds of times per second. A universe where the light from distant galaxies carries the story of cosmic history, written in wavelengths and spectra, readable by anyone with the right instruments and the patience to look. And we found a universe that is, in many ways, deeply mysterious. We don't know what dark matter is. We don't know what dark energy is. We don't know whether the universe is finite or infinite. We don't know what happened before the Big Bang. We've mapped the observable universe with extraordinary precision, but the map is full of blank spaces and question marks. The known is surrounded on all sides by the unknown, and perhaps that's as it should be. The universe has been revealing itself to us for barely 4 centuries, since Galileo first pointed a telescope at the sky. In that time, we've discovered that the Earth is not the center of the universe, that the stars are other suns, that the Milky Way is one galaxy among billions, that the universe is expanding, that it began with a Big Bang, that it's filled with invisible matter and propelled by invisible energy. Each discovery has expanded our understanding and deepened our sense of wonder, and each one has revealed new mysteries, new questions, new horizons to explore. The journey to the edge of the observable universe is a journey without end, not because the edge keeps moving, though in a sense it does, as the universe ages and light from more distant regions reaches us, but because every answer raises new questions, every discovery opens new doors. The more we learn, the more we realize we don't know. And that, perhaps, is the most humbling and exhilarating thing about the cosmos. It is always larger than our understanding, always deeper than our theories, always more beautiful than our expectations. Let your mind wander now. Imagine yourself floating in the void between galaxies, far from any star, far from any world. Nothing but darkness in every direction, except for the faint smudged glow of distant galaxies scattered across the sky like fireflies in an infinite meadow, each one a city of stars, each one a world of worlds, each one separated from its neighbors by millions of light years of empty space. The silence here would be absolute. Sound doesn't travel through a vacuum. There would be no wind, no waves, no voices, just the silence of the void, the deepest, most complete silence imaginable. And in that silence, the light of the galaxies would be your only company. Light that has been traveling for millions of years, light that left its source long before you were born, long before your species existed, long before the Earth itself was formed. Ancient light, patient and tireless, crossing the void at 300,000 kilometers per second, carrying information about distant worlds and distant times. Every photon of that light has a story. It was born in the nuclear furnace of a star, or in the superheated accretion disk around a black hole, or in the hot gas of a galaxy cluster. It traveled through space, through dust clouds and magnetic fields and the expanding fabric of the universe itself, and after millions or billions of years it arrived, at a telescope, at an eye, at a sensor, and it delivered its message. A message about temperature, composition, distance, motion. A message about the universe itself. Astronomy is the art of reading those messages, of listening to the light. And what it tells us is a story of unimaginable scale and beauty. A story that began 13.8 billion years ago in a hot, dense, infinitely small point, and has been unfolding ever since. A story of expansion and cooling, of condensation and collapse, of stars igniting and galaxies forming, of planets coalescing and life emerging. A story that is still being written right now in every corner of the observable universe. And you are part of that story. Not a bystander, not an observer, a participant. The atoms in your body were forged in the cores of stars that lived and died billions of years ago. The hydrogen in your water is primordial, created in the first few minutes after the Big Bang. The carbon in your cells, the oxygen in your breath, the iron in your blood, all were manufactured in stellar furnaces and scattered across space by supernova explosions. You are literally made of the universe. Star stuff, as Carl Sagan famously said, contemplating the stars. And the fact that you can contemplate the stars, that you can look up at the night sky and wonder about the nature of the cosmos, is itself one of the most remarkable things in the observable universe. As far as we know, Earth is the only place where matter has organized itself into beings capable of understanding the universe they inhabit. That may not be true. There may be other minds out there, on other worlds, in other galaxies, looking up at their own skies and asking their own questions. But for now, we are the only known example of the universe becoming conscious of itself. The only known place where the cosmos has developed the capacity to look inward and ask, "What am I?" That question drives all of science, all of astronomy, all of our reaching outward with telescopes and spacecraft and mathematical theories toward the edge of the observable universe and beyond. We want to know what we are, where we came from, how we got here, and where the story goes from here. The answers we found so far are provisional. They'll be revised and refined as new observations come in, as new theories are developed, as new instruments push our view deeper and further. The edge of the observable universe is not the end of the journey. It's a waypoint, a marker that says, this is how far we can see right now. Tomorrow, we might see a little farther, and the day after that, a little farther still. But tonight, let's rest. Let's let the vastness of the cosmos settle over us like a blanket of quiet. Let the numbers, the billions of light years, the trillions of galaxies, the sextillions of stars fade into the background. They'll be there tomorrow. The universe isn't going anywhere. It's patient. It's been here for 13.8 billion years. It can wait for you. Think of the Earth, that small blue rocky world, orbiting an ordinary star in the suburbs of an ordinary galaxy. Think of how improbable it is that this particular arrangement of matter, this particular planet, in this particular orbit, at this particular time, should be the home of creatures who can contemplate the cosmos. Think of how precious this moment is. This brief window of consciousness, this flicker of awareness in a universe that is mostly dark and cold and empty. You are here. You are alive. You are aware. And the universe is spread out before you in all its vastness and beauty and mystery, waiting to be explored. Not tonight. Tonight you rest. But the stars will be there in the morning. The galaxies will still be wheeling through space. The cosmic microwave background will still be glowing, softly, at the edge of everything, and the questions will still be waiting, patient and beautiful and endless. Think of the light that's arriving at the Earth right now, at this very moment. Photons from the Sun, 8 minutes old. Photons from Proxima Centauri, 4 years old. Photons from Andromeda, 2.5 million years old. Photons from distant quasars, billions of years old. And photons from the cosmic microwave background, 13.8 billion years old, the oldest light in existence, arriving at your world right now after traveling for nearly the entire history of the universe. All of this light, from all of these sources, arriving simultaneously, layered on top of one another, a palimpsest of cosmic history, written in photons, and somewhere right now on the far side of the observable universe, a star is exploding, a galaxy is forming, a black hole is growing. A photon is beginning its journey toward Earth, a journey that will take billions of years, a journey that will outlast our sun, our planet, and perhaps our species. But the photon doesn't know that. It doesn't know anything. It simply travels, at the speed of light, through the expanding void, carrying its message, patient and tireless, toward a destination it will reach billions of years from now. Will anyone be there to receive it? Will there be eyes to see it? Instruments to detect it? Minds to understand it? We don't know, but the photon will arrive regardless. It will carry its message regardless. The universe doesn't need us to be beautiful. It doesn't need observers to be vast. It simply is, and we are fortunate, profoundly, impossibly fortunate, to be here to see it. Let your eyes close now. Let your breathing slow. Let the vastness of the cosmos become a kind of peace. The distances are too large to worry about. The timescales are too long to be anxious about. The mysteries are too deep to be solved tonight. All of it can wait. All of it will wait. The universe is patient, and tonight, so are you. Think of the journey we've taken, from the ground beneath your feet to the edge of everything, from the familiar warmth of Earth to the ancient glow of the cosmic microwave background, from the local to the universal, from the known to the unknown. It's a journey that every human being can take, in their mind, at any time. All you need is curiosity and a willingness to be amazed. The observable universe is 93 billion light-years across. It contains 2 trillion galaxies. It's 13.8 billion years old. It's mostly dark matter and dark energy, substances we don't understand. It began with a big bang, and it will end, probably, in a slow, cold, quiet fading. And somewhere in the middle of it all, on a small rocky planet orbiting an ordinary star, a species has arisen that can look up at the sky and understand, at least in part, what it's seeing. That's us. That's you. And that is perhaps the most remarkable thing in the observable universe. The stars are out there. The galaxies are spinning. The cosmic web is shimmering with the light of billions of suns. And the cosmic microwave background is glowing softly at the edge of everything, a gentle reminder of where it all began. Sleep now? Let the universe hold you. You are part of it, and it is part of you. The atoms in your body are as old as the stars. The space you occupy is continuous with the space between galaxies. There is no boundary between you and the cosmos. You are the cosmos, briefly gathered into a form that can wonder about itself. Dream of distant galaxies. Dream of ancient light. Dream of a universe so vast that it takes 13.8 billion years of light-speed travel to cross it, and even then, you've only crossed the part you can see. Dream of what lies beyond. Dream of the unknown, and know that when you wake, the universe will still be here, still vast, still beautiful, still mysterious, still waiting to be explored. Good night, sleep well, and thank you for traveling with us tonight on Neptune Files.